what we tried to do was this particular CTLE, from having the channel response as this, you are able to recover up to 18 dB at 10 gigahertz. So you try to achieve this flat band all the way here, and then this will give us sudden drop. So till your region of operation, you can go. So in case if your system is operating anywhere between 1 and 10 gigahertz and is seeing significant loss, that gets compensated with this flat band. So for example, if you're working at say 2 gigahertz, 1 is here, 2 is here, you're still in a flat band. This very small amount of compensation does not have much value. Same thing you do it at 5, 2, 3, 4, 5. 5 will actually see at least half of it. So 9 to 10 dB can be easily recovered with this. 10, you are able to straight away get a 10 dB recovery. So this is what you will call equalization of the channel. So this is on the receiver side. So this is a quick example to show how when you tune the RS and R knobs, how the gain gets spread. So the DC gain can go from 0, from a negative value all the way up to 2 dB, and your peak you can vary across depending upon where you want to tune it. So this is very layout sensitive. So you have to ensure that all this tuning can be done after the layout is done with a careful understanding of the system. So quick to show, okay, you have shown me mathematically, so show it to me physically. How do you validate that? Easiest way of seeing this. This is a signal transmitted with the various pre-emphasis that is present in your transmitter, and here is a very small I, literally no I present in your receiver that we receive. So how do you recover this data? With the CTLE, you are able to recover by increasing the I. Note the value that we get. Here it is only 10 millivolt, so this is probably about 2 to 3 millivolts. This 2 to 3 millivolts being able to recover, you are looking at 508 to 530. Around 20 millivolt is what you get, the 16. Up to 16 millivolt is what you can bring it up. So 8 times you have been able to increase the gain. Now I did mention, right, there is a metric. Your eye diagram will tell you how good your eye is. So this is what the eye looks when you, the left hand side figure is what the eye looks when you receive it before the CTLE. After the equalization, you get a clear eye opening. From no eye opening to eye opening, this allows you to understand, can you take a decision based on this. Now if you put a decision or an inverter here, if you put sufficient threshold, if you go over the threshold, you will be able to decide that anything above this line is a logical 1. Anything below this 0 is a logical 0. So you can decide.
Is the equalizer an analog circuit?
Equalizer is an analog circuit. This is the equalizer. This is the equalizer. It's an analog circuit. Okay. So if you are looking at, okay, if you are you referring to the digital communication one? So there are some equalizers which are present, but those are at lower frequencies. So at lower frequencies, you can still build it. Effectively, it would be like an FIR filter kind of a thing. So you build a digital DSP-based FIR filter for equalization. It happens at lower frequencies. Yeah, higher frequencies you prefer analog because you do not have digital still running that fast, right?
Get the block for the switch capacitance, because that would also require a second clock source which is very near the transmission frequency.
That is correct. Switching does. Oh, good question. So now, for example, this is a switch which is present here, right? I do not need to turn on this switch at this speed. It is only to tune this one. So it is a low frequency. This is again a low frequency switch to only choose which one do I want. So it is not in the signal part, it is not the high frequency signal switch that I need here. In this particular implementation, you would do that. If you really need to do a switch capacitor, then you are limited by what is the turn on, turn off time of the switch that you use, and that is the maximum frequency that you can work.
So one more thing, you recovered some of the loss using that
Yes.
CTLE. So how much power was burned in this circuit?
Quite a lot of power gets burnt here. So it is again a trade-off. Typically, we are looking at sub-milliwatt applications are also there. More than tens of milliwatt applications are also there, subject to what is the maximum frequency that you are trying to do. So it is always frequency dependent, because as the frequency goes up, there is a non-linear relation with the power, right? It is the hyperbola kind of performance is what you see. So you'll actually see much more power for much higher frequencies. So yes, power burn will be there, but you need that to recover the signal. So it's a trade-off. performance trade-off that will be.
The power may depend on how closer you want to get.
That is true. If you want to get ideal one, you try and burn as much power you will get. But beyond one stage, you will not see the benefit. So you only hit the sweet spot. You can go actually further optimize it, but you do not get a much benefit out of it. So you stop at a place where it's a nice sweet spot and you can work with it.